Hello and welcome to this Python tutorial and welcome to part 10, model selection and boosting. So in this part we will do two things. First, evaluating our model performance, and second, improving our model performance. And then there will be this bonus section about one of the most powerful algorithms in machine learning, which has become more and more popular, and that is called XGBoost. But first, we want to be able to improve the model performance of all the machine learning models we've built in this course. And improving the model performance can be done with a technique called model selection that consists of choosing the best parameters of your machine learning models. Because remember, every time we built a machine learning model, well, we had two types of parameters. The first type were the parameters that the model learned, that is the parameters that were changed and found optimal values by running the model. And then the second type of parameters are the parameters that we chose ourselves. For example, the kernel parameter in the kernel SVM model. And these parameters are called the hyperparameters. So there is still room to improve the model because we can still choose some optimal values for these parameters. But since these parameters are not the parameters learned by the model, then we need to figure out another way to choose these optimal values for these parameters, for the hyperparameters. And that's one of the powerful things we'll do in this part 10, and that will be through a very efficient technique called grid search. But before we start grid search, we need to optimize our way to evaluate our models. Because so far, what we did is split our dataset between a training set and a test set, and we trained our model on the training set, and we tested its performance on the test set. That's a correct way of evaluating the model performance, but that's not the best one, because we actually have the variance problem. The variance problem can be explained by the fact that when we get the accuracy on the test set, well, if we run the model again and test again its performance on another test set, well, we can get a very different accuracy. So, judging our model performance only on one accuracy on one test set is actually not super relevant. That's not the most relevant way to evaluate the model performance. And so there is this technique called k-fold cross-validation that improves this a lot, because that will fix this variance problem. And how will it fix it? It will fix it by splitting the training set into 10 folds when k equals 10, and most of the time k equals 10. And we train our model on 9 folds, and we test it on the last remaining fold. And since with 10 folds we can make 10 different combinations of 9 folds to train the model and 1 fold to test it, that means that we can train the model and test the model on 10 combinations of training and test sets. And that will already give us a much better idea of the model performance, because what we can do afterwards is take an average of the different accuracies of the 10 evaluations and also compute the standard deviation to have a look at the variance. So eventually, our analysis will be much more relevant. And besides, we'll know in which of these 4 categories we'll be. Because if we get a good accuracy and a small variance, we'll be on the lower left one. If we get a large accuracy and a high variance, we will be on the lower right one. If we get a small accuracy and a low variance, we will be on the upper left one. And eventually, if we get a low accuracy and a high variance, we will be on the upper right one. So this k-fold cross-validation is very useful, and besides, our performance analysis is much more relevant. So let's start with this k-fold cross-validation, our first technique of model selection. So since we already built a lot of models, we're not going to build another one. We're going to use one of the models we built and apply k-fold cross-validation on it. And so the model we're going to use is this kernel SVM we made in part 3 classification, and that, remember, we used to predict if the customers are going to click on the ad on the social network to buy yes or no the SUV. So the model is already built and we already have everything. So what we're going to do is take the whole model and we are going to add a new section code inside of it. That is going to be, of course, the section code that will implement k-fold cross-validation. So before we start doing it, let's pick the right folder as working directory. So we go to File Explorer, Machine Learning A to Z. we're now in the last part of this course. Congratulations for reaching it. Part 10, model selection and boosting, and section 48, model selection. All right, make sure that you have the social network at CSV file, and if that's the case, you're ready to go. All right, so now where do we apply the k-fold cross-validation code section? Well, since that consists of evaluating the model performance, well, the most relevant location to put it is right after we build our kernel SVM model. That is right after we build the model. And actually in this code here, we have the predictions of the test set results and the confusion matrix. That is actually a first way of evaluating the model. But as said at the beginning of this tutorial, this is a correct way of evaluating the model, but not the best one. And in today's tutorial, we are introducing a much better way to evaluate our model. And so let's put it right after this section, as in a more advanced performance evaluation method. And so we're going to call this section applying k-fold cross-validation. All right, and now let's start. So the first thing is, of course, to import the right class for the job, and more precisely the right function. And this function is called cross-val_score, and it is imported from the model selection module. That is the same module that we use here to import the train test split function to split the data set into the training set and the test set. So that's the same. So let's do it. Let's import the cross-val_score function. So from sklearn.model selection, here we go, import cross-val_score. All right, that's done. And so now let's apply k-fold cross-validation on our training set. So before applying it, we need to understand what it will return. Well, it will actually return the 10 accuracies for each one of the 10 combinations that will be created through k-fold cross-validation. So since each combination is composed of 9 folds to train the model and 1 fold to test it, well, as said before, we'll get 10 combinations and therefore 10 accuracies. And so the first thing to do is to define a vector that we're going to call accuracies, and that is going to be the vector that will get the 10 accuracies that will be computed through the 10 combinations created through k-fold cross-validation. So eventually this accuracies vector will be composed of 10 elements, and these 10 elements will be 10 accuracies to evaluate our model. Alright, so now what we have to do is to use this cross-val_score function to apply k-fold cross-validation very efficiently. So cross-val_score and then parentheses, and then we input the different parameters. So let's see what those parameters are. I'm going to press Command I here to inspect this cross-val_score function. So let's see, the first parameter is estimator. So that's your model, that's your classifier. And how did we call our classifier? We called it classifier. So here we have to input estimator equals classifier. All right, so first parameter is our estimator classifier. Then the second parameter is X, the data to fit. So that's actually the training set, because k-fold cross-validation is applied on the training set, but that is the matrix of features part of the training set. So therefore, X will be xtrain, because our training set is composed of xtrain, the matrix of features, and ytrain, the dependent variable vector. So here we add X equals xtrain. All right. Now the next argument, as you might have guessed, is y. And y, of course, is the dependent variable vector of the training set. As you can see, it is set to be the target variable to try to predict in the case of supervised learning. And that still corresponds to the training set, so of course that is ytrain. So here we add y equals ytrain. All right. Now next argument. Next argument is groups, but that's not actually important here. Same for scoring, not the most important. What we are mostly interested in is this CV parameter, because the CV parameter is actually the number of folds you want to split your training set into. And the most common choice for this CV number is actually 10. Most of the time you'll use tenfold cross-validation, because tenfold cross-validation means that you'll get 10 accuracies, and 10 accuracies is actually enough to get a relevant idea of the model performance. So here we will add CV equals 10. Perfect, and that's actually all we need to input here to perform an efficient k-fold cross-validation. If you are working on a very large dataset, what you can do is add this njobs parameter and set its value to -1, because -1 means that you will use all the CPUs on your machine, and therefore your k-fold cross-validation will run faster. But here that's fine. The point of this tutorial is not to work on a large dataset. It is rather to learn how to apply k-fold cross-validation. So we are ready to get our 10 accuracies, and therefore we'll get a much better idea of our model performance. So let's do this. Let's select all the lines of code from here to the top, and that will run the preprocessing phase, fit the kernel SVM model to the training set, predict the test set results, making the confusion matrix so that the first performance evaluation method, and there is our more advanced performance evaluation method, k-fold cross-validation, more precisely tenfold cross-validation, and let's see what we get. So let's press Command and Control plus Enter to execute. Here we go. We just have a data conversion warning because some integers were converted into floats. That's fine. Now let's see our accuracies vector in Variable Explorer. So here it is, accuracies, and if we open it, we get the 10 accuracies of this k-fold cross-validation process. And so what do we see here? We can see how it was relevant to do this, because the first accuracy is 80%, but then the second accuracy is 96%, and then 80% again, and then 93%, 86%, 83%. So that clearly shows what I was telling you at the beginning of this tutorial, that is, when you test the performance of your model on one test set, well, you get an accuracy, but then when you test it again on another test set, you can get a very different accuracy. And so evaluating the model performance on one test set is not very relevant. And now with k-fold cross-validation, we are testing it on 10 test sets, and therefore now what we're going to do is take the mean of all these 10 accuracies, and that will give us a much better idea of the average model performance of our model. So let's press OK, and let's get this average. To get this average, it's actually very simple. We just need to take our accuracies vector. Here we go. Then just add a dot, and then just add the mean function. And that's it. Just running this will give us the mean of the 10 accuracies of this accuracies vector. So we get 90%. That means that the mean of these 10 accuracies here is actually 90%. And so in conclusion, this 90% accuracy is the relevant evaluation of our model performance. It is not 80%, it is not either 96%, it is the mean of at least 10 model evaluations, that is 10 accuracies. So perfect. And if we want to push the analysis further, what we can do is compute also the standard deviation of this accuracies vector. That will tell us if there is a high variance or a low variance. So that's also very interesting. And to do this, we do the same. We take our accuracies vector, then we add a dot, and then we use the std function that will give us the standard deviation of this accuracies vector. So here we go. Let's run it. And we get a 6% standard deviation. So what does that mean? That means that the average of the differences between the different accuracies that we'll get when evaluating our model performance and the average accuracy, that is 90%, is 6%. So that's actually not a too high variance. That's okay, because that means that when we evaluate our model performance, well, most of the time we will be around 84% and 96%. So eventually, that means that we are in this low bias and low variance category. So that's pretty good. And now, congratulations, you have a much more advanced way of evaluating your model performance in your data science toolkit. But you'll see, in the next tutorial we'll see a very powerful technique that will help us choose the optimal hyperparameters of any machine learning model we build. So I look forward to doing that in the next tutorial, and until then,